Sir Isaac Newton proved Kepler's laws of planetary motion, and this was published in his famous works, the most famous work that Newton did, known as the Principia in Latin, in 1687. Uh, the English version of this would be called Mathematical Principles of Natural Philosophy. And yes, Newton was English, but in those days you published academic works in the Latin language. So, anyway, so that's where Newton printed this material of proofs of Kepler's laws. So really, he changed them from being laws to mathematical theorems, essentially. And really, the only two things that we need to use to make these proofs, starting points, we do have two premises. And these are Newton's laws themselves. Newton's laws of planetary motion. Newton's second law of motion. Didn't need to say planetary motion, actually. Just Newton's law of motion that, F equals ma, everybody's familiar with. In this particular case, notice I've written it in vector form, right? The acceleration of an object is proportional to the force applied, both in terms of direction and magnitude here. And the other law is Newton's law of universal gravitation. And the law of universal gravitation, if you know this one, and actually you've encountered it before, certainly in Calc 2, this was brought up, the inverse square law for gravity, so that the magnitude of the force is proportional to 1 over the distance squared. Now we've got these two different ways of writing this that I just want to clarify. And actually we dealt with this a little bit in class before. This doesn't look like inverse squared, it looks like inverse cubed, but that's because we've got, this is the vector between the two objects, right? And so, in this form I changed it so it looks more like the familiar inverse square law, where u is in fact just the unit vector. I can clarify some of that down here. Okay, right, so our force vector, little m and big M are the masses of the planet and the sun, or actually can be the masses of any two objects gravitationally, but in this case it's the planet and the sun. Big G is the gravitation constant. In this case, the sort of fancy R is the magnitude of the vector between the two objects. And then finally, as I said, the U vector is the unit vector in the direction of the R, which is what corrects for the two different notations. And we'll use both forms of this when we go through the proof. But Newton's proof of Kepler's laws of planetary motion require only these two laws themselves, okay? And so that's what we're going to use along with understanding of some vector stuff. So we need to, first of all, look at, a diagram of what's going on here. The vectors here, we've got our planet orbiting around the sun. We've got a velocity vector indicating the velocity here. We know that our position vector is going to go straight from the sun out to the planet because we're going to put the sun at the origin, actually, for this particular situation. It's going to work out best for us. So this becomes the position vector of the planet, describing the motion. And then our acceleration vector, we know, is directly in line with back to the sun because, of course, that's the direction that the gravity is pulling it in. And then just keep a reminder here that the velocity vector is, of course, the derivative of our position vector, and the acceleration being the second derivative of the position vector. So, these relationships are going to be important here. All right, so to show the motion of the planets is in the plane is the first step we're going to do to prove this first law. Remember, the first law is that the planets are orbiting in elliptic orbit. And so the first thing is actually to show that the motion is in fact planar. It's in a single plane, okay? And the first thing to do is we're going to have to equate these two Newton's laws that we said we're going to use, the gravitation law and Newton's second law of motion. And we'll continue that in the next video.